control the speed of a 120-volt single-phase motor automatically, several methods can be employed. Firstly, consider using solid-state relays, or SSRs, with a built-in ramp timer. The advantages of this approach are that it is cost-effective, easy to implement, and provides precise control over the motor's speed. Secondly, you could use motor speed controllers, or MSCs. These are electronic devices specifically designed for controlling the speed of alternating current motors. They offer a wide range of features, including ramping capabilities, proportional integral derivative, or PID control, and torque limiting. Thirdly, a variable frequency drive, or VFD, with a direct current or DC link can be used. This involves converting the 120 volts alternating current to direct current, then inverting it back to alternating current with a variable frequency. This method provides smooth and precise speed control but may be more expensive than other options. Fourthly, consider phase angle control. This method involves adjusting the timing between the motor's stator and rotor windings to vary the speed. It is simple and cost-effective, but it is less precise than other methods. Fifthly, mechanical speed reducers, such as gears or belts, can be used to reduce the motor's speed. This provides a simple and durable method of speed control, but it does not allow for ramping. When selecting a method, several product recommendations can be considered. For SSR with ramp timers, Automation Direct SSR2525D is a suitable option. For motor speed controllers, consider the Automation Direct GSON or GSG series or the Bolt or BDS-300 series. For VFD with direct current links, the Escobar P1000 or A1000 series or the Allen Bradley PowerFlex 525 series are viable choices. When implementing these methods, keep these tips in mind. Use the soft start circuit to reduce torque transients during motor startup. Choose a method that aligns with the required precision, performance, and cost constraints of the application. Consider the motor's duty cycle and thermal characteristics to avoid overheating. If using a mechanical speed reducer, ensure it is rated for the required torque and speed. Let's delve deeper into each of these methods to provide a more comprehensive understanding. Solid-state relays with ramp timers offer a straightforward solution for controlling motor speed. The ramp timer allows you to gradually increase the voltage applied to the motor, resulting in a smooth acceleration to full speed. This minimizes stress on the motor and connected equipment. Many SSR also include features like current limiting and overvoltage protection, enhancing the safety and reliability of the system. Motor speed controllers provide more advanced control capabilities. These devices typically use pulse width modulation, or PWM, to regulate the voltage and frequency supplied to the motor. This allows for precise speed control and the ability to maintain constant torque over a wide speed range. PID control is often included in motor speed controllers, enabling automatic adjustment of the motor speed to maintain a desired set point. Variable frequency drives with direct current links offer the most sophisticated method of motor speed control. By converting the incoming alternating current power to direct current and then inverting it back to alternating current with a variable frequency, VFD can precisely control both the speed and torque of the motor. VFD also offer a range of protective features, such as overcurrent protection, overvoltage protection, and undervoltage protection. Additionally, VFD can improve energy efficiency by reducing the motor's power consumption at lower speeds. Phase angle control is a simpler and less expensive method of motor speed control. It involves adjusting the firing angle of a triac or silicon-controlled rectifier, or SCR, to control the amount of voltage applied to the motor. This method is suitable for applications where precise speed control is not required. However, it can generate harmonic distortion and may not be compatible with all types of motors. Mechanical speed reducers provide a robust and reliable method of reducing motor speed. Gears and belts are used to transmit power from the motor to the driven equipment at a lower speed. Mechanical speed reducers are often used in applications where high torque is required at low speed. However, they do not allow for ramping or variable speed control. In summary, the choice of method for controlling the speed of a 120-volt single-phase motor depends on the specific requirements of the application. Solid-state relays with ramp timers offer a cost-effective and easy-to-implement solution for basic speed control. Motor speed controllers provide more advanced control capabilities, including ramping, PID control, and torque limiting. Variable frequency drives with direct current links offer the most sophisticated and precise method of motor speed control. Phase angle control is a simpler and less expensive option for applications where precise speed control is not required. Mechanical speed reducers provide a robust and reliable method of reducing motor speed. Remember to consider factors such as cost, performance, precision, and safety when selecting a method. Always consult the motor manufacturer's specifications and applicable electrical codes before implementing any motor control system. Furthermore, it's important to consider the specific characteristics of the motor being used. Different types of motors, such as induction motors, universal motors, and synchronous motors, have different speed-torque characteristics and may require different control methods. For example, universal motors, which are commonly found in appliances like blenders and vacuum cleaners, can be controlled using simple phase angle control circuits. Induction motors, which are widely used in industrial applications, typically require more sophisticated control methods such as VFD or motor speed controllers. Synchronous motors, which are used in applications where precise speed control is critical, often require specialized control systems that can maintain synchronization between the motor and the power supply. In addition to the control method itself, it's also important to consider the components used in the system. Solid-state relays, motor speed controllers, and VFD are available in a wide range of ratings and features. It's essential to select components that are appropriately sized for the motor being controlled and that meet the specific requirements of the application. For example, if the motor is subjected to frequent starts and stops, it's important to select a solid-state relay or motor speed controller that is rated for high inrush current. If the motor is operating in a harsh environment, it's important to select components that are protected against dust, moisture, and temperature extremes. When implementing a motor control system, it's also important to follow all applicable safety precautions. Motors can generate significant amounts of torque and can be dangerous if not properly controlled. Always disconnect the power supply before working on any motor control system. Use appropriate personal protective equipment, such as safety glasses and gloves, when working with electrical equipment. Ensure that all wiring is properly insulated and grounded. Never operate a motor control system that is damaged or malfunctioning. In addition to the methods and components discussed above, there are also a number of other factors that can affect the performance of a motor control system. These factors include the voltage and frequency of the power supply, the load in the motor, and the ambient temperature. It's important to consider these factors when designing and implementing a motor control system to ensure that it operates reliably and efficiently. For example, if the voltage of the power supply is too low, the motor may not be able to develop sufficient torque to start or run properly. If the load on the motor is too high, the motor may overheat and fail. If the ambient temperature is too high, the motor may direct and produce less power. In summary, controlling the speed of a 120-volt single-phase motor automatically requires careful consideration of a number of factors. The choice of method, the selection of components, and the implementation of safety precautions are all critical to ensuring a successful and reliable motor control system. By understanding the principles of motor control and by following best practices, it's possible to design and implement a system that meets the specific requirements of the application. Furthermore, consider the use of feedback control systems for enhanced precision. Feedback control involves using sensors to monitor the motor's speed and adjust the control signal accordingly. This can compensate for variations in load, voltage, and temperature, resulting in more accurate and consistent speed control. Encoders are commonly used as speed sensors and feedback control systems. An encoder is a device that provides a digital signal proportional to the motor's rotational speed. This signal can be used by a controller to adjust the motor speed to maintain a desired set point. There are two main types of encoders: incremental encoders and absolute encoders. Incremental encoders provide a series of pulses that indicate the direction and amount of rotation. Absolute encoders provide a unique digital code for each position of the motor shaft. Absolute encoders are more expensive than incremental encoders, but they offer higher accuracy and are less susceptible to noise. In addition to encoders, other types of sensors can be used to provide feedback for motor control systems. Tachometers are devices that generate a voltage proportional to the motor's speed. Current sensors can be used to monitor the motor's current consumption, which can be used to estimate the motor's torque. Temperature sensors can be used to monitor the motor's temperature and prevent overheating. The choice of sensor depends on the specific requirements of the application. Another important aspect of motor control is the selection of a suitable controller. A controller is a device that processes the feedback signal from the sensor and generates a control signal that is sent to the motor control device, such as a solid-state relay, motor speed controller, or VFD. Controllers can be implemented using a variety of technologies, including microcontrollers, programmable logic controllers, or PLCs, and dedicated motor control integrated circuits, or ICs. Microcontrollers are small, low-cost computers that can be programmed to perform a wide range of control tasks. PLC are industrial-grade controllers that are designed for use in harsh environments. Dedicated motor control IC are specialized chips that are designed specifically for motor control applications. The choice of controller depends on the complexity of the control task and the specific requirements of the application. Finally, it's important to consider the power quality of the electrical supply when designing a motor control system. Poor power quality can cause a number of problems, including motor overheating, reduced motor life, and erratic motor behavior. Power quality problems can be caused by a variety of factors, including voltage sags, voltage swells, harmonic distortion, and transient voltages. To mitigate power quality problems, it's important to use appropriate power conditioning equipment such as surge suppressors, line filters, and uninterruptible power supplies, or UPSs. Surge suppressors protect the motor control system from transient voltages caused by lightning strikes or other electrical disturbances. Line filters reduce harmonic distortion caused by electronic devices. UPS provide backup power in the event of a power outage. In conclusion, automatically controlling the speed of a 120-volt single-phase motor is a complex task that requires careful consideration of a number of factors. By understanding the principles of motor control, selecting appropriate components, implementing safety precautions, and addressing power quality issues, it's possible to design and implement a system that meets the specific requirements of the application. Remember to consider factors such as cost, performance, precision, and safety when selecting a method. Always consult the motor manufacturer's specifications and applicable electrical codes before implementing any motor control system. By carefully considering all of these factors, you can design and implement a 120-volt single-phase motor control system that meets your specific needs and provides reliable, efficient, and safe operation.